So my name's Jamie Riden. I'm doing this talk on it's suggestion from one of my younger colleagues, fantastic crypto failures and where to find them. Basically, how to spot cryptographic bugs in source code. There's a whole lot of stuff to go through because you don't know why. You need to know how something is meant to work before you can tell how it's going to fail when it fails. So it's going to be quite a lot of background before we actually get to anything more interesting. That doesn't do the same thing, right? That's not. Sorry. So I've been messing about with computers for a very, very long time now. I guess notably I've been a developer. I've been a sysadmin. I've been blue team. I've been IT security, like GRC type risk assessment type things, and I've been a pen tester. So I've been involved at basically every stage in the bug report process from every side of the process, which has been really helpful for some of these things. And I guess I got into this because of a previous interest in password cracking, and then this kind of some of those things that weren't passwords, but they needed decrypting in various things like web application tests and red teams and so on. So what's this for? I mean, the bugs I'm going to talk about aren't actually very complicated, but they seem to really scare a lot of people off. They're not really that complicated. You can, if you get source code, you can find them too. So if I can, you can basically. So good ways of getting source code, if you've got C# or Java, the example I'm going to come to later is Java, and you can just really load it into JD GUI, and it gave me basically the exact source code I already had that was compiled. It hadn't been obfuscated, so that was really trivial. If you're working with a client, it's really worth asking them for the source code because it does essentially save them money because you're more efficient. You can find bugs in the code and then test them on the test system, rather than having to do this black box testing approach, which seems to be where we are as an industry, but it's certainly not the most efficient. A lot of clients don't have a problem or haven't considered giving you access to source code. Some of them can be persuaded. Sorry, is this advancing without me? Which could be a problem. Anyway, so I want to say thank you to basically two people who sort of inspired me in this regard. Tao and Mario, you probably don't know, but we rocked up to do a web application test, and they immediately just pulled down the jar file, started decompiling it, found loads of bugs in the web application that way, rather than doing it obviously the way we all love using Bert. You also do need a decent amount of time to look at any of these things. So if you've got a 3-day web app, you're not going to be able to do some of these things. And then thanks very much to Kerry for proofing this. And then the person I found, I was doing a red team test when I found this particular bug. Phil Kopp, who told me to move on past the crypto bug. We had other things to do, and it was entirely correct, which is good because you can just disappear down a rabbit hole, and then you haven't done the actual important bit of your red team report that they wanted you to look at. So we're going to look at some do's and don'ts for crypto, and then if you've got source code via any of these means, you can look for where those sort of don'ts are happening, how to fix them, and then we'll go through some examples of attacking these things. So other things I should probably say, it's really hard to get right from a dev's point of view. The dev's probably just been told to do encryption. They've done encryption, tick on the product, whatever. That's probably the kind of level they're working at if they haven't done it before. So the other thing is, if you're trying to protect secrets on a computer and then reuse them later, so this is the example, the help desk software I was looking at some point it's got to decrypt that password and replay it. So you're kind of doomed because you do have to decrypt it at some point, which means that someone else can decrypt it at some point. You can make it harder, but like with DRM, you can never really stop people from getting it. From a personal point of view, it's a nice thing because no one knows you failed. No which is, I think Mark Dad said this as well. If you try and don't get anything, no one knows, which is great. And in most cases, if you have cracked it, you immediately know that you've solved the thing. You get a sensible decrypt out. So, like I said, the DRM, if you're encrypting any data on a machine and then you have to decrypt it on the machine, obviously the attacker can get that if they have a copy of the hardware or something. They will always be able to decrypt it. You may be able to make it harder. You just need to make it so an attacker can only attack one instance at once. So, like an example, a recent .NET app I was looking at had it prompted you for a password which was generated through some horrible algorithm. You could just put it back, patch the .NET code with DNS Spy to print out the answer, and then just run it. It says that's the answer because it has to compare. It's gone to a lot of work to generate the password, but at some point it has to do an if your password equals the password I'm thinking of. At another point, you can just get it to print out. So not all of the things are entirely solvable. So in the very basics, Kirchhoff said in 1983, assume your algorithm is public. So that's AES CBC. Everyone knows that you're going to be using something like that. The key is the only bit that must remain secure. And so the corollary of that is security by obscurity is not really security, it's only economics. So you just, like I say, with GRM, you can make it harder for people. But in some cases, if you're doing this, you can't make it impossible. So, yeah, in these terms, picking a sensible cipher scheme like AES, CPC, PKSDS5 padding, that's literally the baseline. So you see some things like, we've got 256-bit military grade encryption. It's that is literally the least thing you have to do here. It's everything else on top of that. Another one from Moxie Marlinspike, it says basically, if you've got any data coming in, you must verify the message authentication code before you try to decrypt that data and do anything with it. Otherwise, very bad things will happen. And he's got a list on his website of various very bad things that have happened when people have done that. Obviously, he wrote Signal, I believe. And I think probably the last one is just keep it simple, because cryptography is quite complicated. If you try to make it overly complex, you're probably going to end up shooting yourself in the foot. And then there's the quote from Brian Koenig, and so debugging is twice as hard as writing the code. So if you overcomplicate your code, you're going to get into all sorts of horrible little edge cases like Crash FTP, where you could just give a AWS SIG string username and no password, and it would just let you straight in. Because if you look at the bug report, it was a very convoluted flow with lots of ifs in, and it's just, you should have broken out completely differently, and ideally not overloaded one thing with all the different authentication types. So basically, I think the moral is don't be afraid of seeing AES 128, whatever. That's not the hard bit. It's the hard bit is sort of setting up everything else so that works properly. So I'm going to just go over some of the basic cryptography, which shouldn't be too painful, hopefully. So I'm going to start out with password hashing. So the naive way, you don't want to store a plain text password, obviously. You want to store a hash. So someone back in the day took MD4 as a good thing to use. Now we know that's not very good, because MD4, I've got an older graphics card which can do 100 billion guesses per second against MD4. Because of the construction, I can also attack, say, 50 million people in the domain. If you have a domain that big, you can guess one password all at once for all those users. And equally, you could just build a dictionary of really common passwords and their hashes and just look it up. Anyone know why I picked on MD4? It's NTLM. So that is still with us today, unfortunately. It's not as bad as LM, but it's not good. So in fact, writing to disk is even pointless because we can generate these things much faster than we can read them off disk. But we still need what's called the salt to individualize the hash. In terms of hash functions, there's a whole lot of other things that are wrong with MD4 apart from being quick. So then someone had the idea, which came along, I think, with Descrypt on Unix, of having a salt. So this is kind of not a helpful term, maybe, but it's some data, a random data you put with the password and you store it with the hash, so you can't attack two different users at the same time. They've got different salts, so the computation is going to be different. So that means you've got like 10 people on your domain with the password summer 2025. You can only attack one of those at a time. So that gets rid of one of the major problems of just using MD4 as a hash. And then with Bcrypt, I think came in cost factor. So because obviously computers are getting faster and faster, they wanted to be able to make the hash harder as computer hardware gets better. So they introduced a cost factor, which is the second parameter. You have $2a, meaning Bcrypt, and then $12, which is the cost factor. In this case is 2 to the power of 12, so that's 4 times as hard as $10. And it just means that obviously every time people change passwords every now and then, and you can just increase that cost factor. So the idea is essentially you just want to not quite annoy the user, so like maybe 100 milliseconds to compute the hash, which a user won't notice on the web page load, but an attacker very much, obviously, it will really frustrate them. So with those two sort of innovations, you've gone from NTLM, where you can do 100 billion guesses a second against all domain users at the same time, and then Bcrypt with a good cost factor, you might be, a couple of thousand guesses per second, and that's against one person at a time because the salt's in there. Right, so encryption is basically, we want to make the message unreadable to everyone except people we give the message to. So symmetric encryption generally turns into a problem of you need to make sure both ends have the same key, because that's obviously the hard bit. The actual encryption then is pretty straightforward. Public key, we don't see so much in code reviews and stuff. It generally turns into a problem of people leaving the private keys lying around on disk. I've seen a private key on an internet router, which is obviously just waiting to be taken off and used for malicious purposes. It was a private key for a SSL signing certificate for a domain that shouldn't have been on the router. But in general, public key is, people don't generally go for that, so we don't see that as much. So if we're talking something like AES, the naive way would be just to encrypt one block at a time. You've got your key, you've got your data, whatever block size, maybe 128 bits, just bang, bang, bang. That's the Wikipedia diagram. So that would seem like quite a reasonable way of doing it, but unfortunately, like obviously most human-generated data has patterns in it of some sort, and this does not sort of really get rid of any of those patterns from the user's point of view. This is the Wikipedia example. That's Tux the penguin encrypted. It's like, well, that's not really good enough for most purposes. Like if it was a floor plan, it would still be pretty much readable. The case where it is okay is if you sort of got a key encrypting key. If you generated some pure random data, then you can use that because it doesn't have any patterns that you might need to obscure. So the next thing to come along is cipher blockchaining, where you feed in the input data again, as it were. So this does destroy any patterns that were in the data. Now Tux the penguin just looks like noise, essentially. So that's kind of the minimum you should be doing in anything. So if you're looking at source code, you can just literally grep with AES-ECB, and you're like, that's probably wrong. There's probably something wrong there. Not necessarily easy to exploit, depending on what the data is, but you may find that then they've made other sorts of errors and used other poor choices of algorithm. So in cipher blockchaining, each block of plain text is XORed with the previous ciphertext block, so that sort of destroys all the data. But obviously, we've got to feed in something at the start before we've processed any data. So that's essentially block 0, which gets fed into the next XOR, and that's called the initialization vector. That gets stored along with the encrypted thing, much as the salt gets stored with the hashed password. Because obviously you can't generate it. And again, it kind of makes the two encryption operations different. So if you encrypt the same thing twice, they should have different IVs, and therefore they should look different. So yeah, just to recap on that, there's a load of ways of just encrypt it that are not very effective, even though they do encrypt it. And like I said, you see people saying they've got military grade 250 AES, and it's like, that's fine, but if your key's written down in the source code, it doesn't do you any good at all. So it's really important to know the purpose of salts and initialization vectors and make sure that everything is like random and not repeated. So then I'm going to go into a few examples of what I've seen that has actually gone wrong. So this was I guess one part of a 3-part CV, all in the same piece of software, where they'd managed to make sort of three mistakes, really, where they should have. I mean, there should have only been one mistake that could have been possible, but they'd varied the scheme slightly. So we were doing a red team. We found some backup files which had encrypted passwords in them, and obviously that's like, yes please, because this software goes and polls all the other computers in the organisation. Therefore, that's of considerable interest to us to reverse these. We in this case we decompiled it with JD GUI. It was Java code. It literally just came out as if like a nicest Java you've ever seen. All the symbols still there, everything, so it hadn't been obfuscated. It was literally like 5 minutes work, and most of that was waiting for the Java files to load in. So looking at these two encrypted messages, from what I've said just now, you can see there's something wrong. If those two pieces of data are encrypted and they have the same lead in, they've not been changing the IV. You can see that straight away. And in fact, if you look at the code, it just says default key, get it from a property file, crypt default key, get the salt, by which they actually mean IV in this case, and use that. So initially we thought all the encryption operations were just using a single IV and salt, which obviously makes that job very easy to decrypt everything. So if you're kind of pushed for time and you're trying to reverse this, you can just take the Java file they're using and kind of what I call link to it. I'm sure it's not called linking in Java. But essentially I took their own code and wrote maybe a 10-line program to call that same routine that they were calling, and then we get to decrypt their stuff. Now, these guys were using GCM, which is Galois counter mode. That's an authenticated cipher. AEAD is the terminology, but it means basically if it had been like AES CBC, you would get a decrypt. You wouldn't know if that decrypt was correct or not until you tried it, because it might be a random password. Now, with AEAD, you get an exception if you got the wrong key, so you know it's right, which is quite nice. So, how should this be fixed? Well, the key should not be constant. In particular, it shouldn't be constant across all the instances of the application in the whole world. That's really bad. If you have to have a constant one, generate it at install time. And yeah, if you're doing that, use a cryptographically safe random number generator. Cryptographic strength is the acronym. But essentially not, C random is not what you want. Java secure random, as you'd expect, does what you want. You could then store it in DP API in Windows, or maybe if you want to be able to take this thing and back it up and put it onto a different machine, maybe you get the user to enter a password and use that with a key derivation function. So the other thing is the IV shouldn't be constant. We've seen that it obscures. It obscures patterns in the input data for encrypting, but for anything that's kind of stream ciphery like GCM, it can be absolutely catastrophic, which we'll get to as part 3. If you have to generate a key from user input, there's functions that you should use, like pbkdf2, which is KDF is a key derivation function, or argon2 is the modern one. So yeah, any of those options to not have a key which is fixed in the source code. So I've done a demo of this, which is not really much to look at because it's just telling you it's decrypted the thing and that's the answer. But that program is only about, it will fit on my screen, to be honest. So yeah, we're using their code that already exists to decrypt that data. So as well as having this kind of default key scheme, they also had a key derivation function they'd written, which it was, I guess, less than ideal. So it took a value from the database init code and it XORed it with a 8 hex digit number. Unfortunately, the first 4 of the hex digits were shared, so they just went to 0. So immediately you've only got a key space of FFFF, which is not big enough. If it only does the maths, that's not big enough even for an online secret. Also, again, you've got magic numbers, secrets in source code. So that was the computation. And certainly in a case of my test install, you ended up with a value between 0 and 65,000, which is just not enough entropy if you've got a 128-bit key. So like normal AES, you should be using an 128-bit random number. That's what it's for. So I have actually slowed this down a lot. It will be searching through the key space from 0 upwards. So I should also mention here, they're turning it into a string. And if anything goes wrong, like init code isn't defined, it just comes out as 0, which is obviously not the failure case you want. So yeah, here's the demo. So this will do basically the same thing, but instead of using the fixed key, it's counting up from 0 to 65,000, then turning it into a string because that's what it takes as a parameter, and then it's come out as nearly 20,000, and we've got a decrypt. And again, we know that decrypt is correct because we've got exceptions when we try to decrypt the other previous sort of 19,000. So we know that is definitely correct. So that was initially we thought everything was using the fixed key, then we found that some of the things were using this other key derivation scheme. So this is not much harder to crack than the first one was. It's marginal. So I had to fix this one. If you are doing a key derivation, you need to use like a real key derivation function. There's been a number of them proposed and knocked down. You can see we're on PBKDF2, presumably PBKDF1 was flawed in some crucial way. So it takes it's a bit of a mouthful. It takes what they call the pseudo-random function, which in our case, for example, is hmax-sha1. It does something that one of the properties of hash functions is it mixes everything up. So like WPA2 uses hmax-sha1, takes your passphrase, takes your SID, 4096 iterations, which is not enough these days, but there we are, and it produces a key length of 256. So that's kind of an acceptable way of doing it. It would, it at least would get your entropy spread over the whole key space rather than confining it to this tiny, tiny little region. So in C#line, that's called RFC 2898 derived bytes. That's the standard. And again, you want to set the iteration count so as just to not quite annoy the user. when they type their password. It defaults to 1,000, which is just nowhere near enough. OWASP recommend, for example, 600,000 iterations with a PPKDFT which makes SHA-256, and then like in 2 years' time they'll be recommending maybe 900,000. So all of this will turn a rather than some homebrew scheme with XOR, use a genuine like proper way of doing it. So we've looked at salts and initialization vectors, and then we also have nonces, which is going to come up with when we get to GCM, which you could probably get away with making it random, but what it really should be is non-repeating. And for most of us, obviously, a randomly generated number will not repeat on the kind of amounts of data we're looking at. It will in some applications, and you will have to think about things separately then. So another thing we came across was a key where they tried to make it random, but hadn't quite succeeded. So they'd use rand, which is not what you should be using, because it doesn't. The way most C libraries do it is linear shift feedback register, and that is absolutely not secure way of doing it. It's too predictable. What made that actually not even matter is they seeded rand at the start time of the service, and the service was installed to start of boot. So you knew the time was going to be less than like 1,000. And obviously then you can just go through all those possible values. Don't make life hard for yourself. Literally take the same, I think it was Linux based, so we just ran it on Linux. It's like, well, you just use the same libc. We don't have to understand how it's broken. We know it's broken. We can just go through all those. We can go through all those things and just literally emulate the same thing that the code is doing. So we go through 60,000 values. We seed the random number generator with that time, which should be a time rather than a thing here. And then we try to do the auth. So this obviously comes up fair. There's very strong parallels with the poor key derivation because we know the search space is tiny, and when we know it, we can just move through that smaller search space. So it was something like amazingly unhelpful. Sorry. This is some code that I wrote just to illustrate the problem. So I did get tick count mod 131072 because I couldn't be able to reboot the thing every time. But it's essentially doing the same thing. Your API key, in this case, is generated using a number between 1 and 130,000 as the random seed. And then it looks... this is just generating it. So obviously this, from the outside, this looks very complex and random, which is all very well. But then if you know how it's being generated, you can simply search through this restricted search space. Sorry, that's the same. As I say, we follow that 0 to 60,000 odd. This is printing every 100th one, and then you can see it's come out on the 45,000th guess. And it's found that because, again, the search space is just completely restricted on what it should be. So yeah, this particular service, my colleague found this and went, oh, that's a feasible offline attack. It's like, and then we tried it online, and it was maybe 1,000 tries, 1,000 and 1,500 to get the API key, which was related to authentication. So that's obviously really bad, but just looking at the outputs, you wouldn't really be able to tell. So if you have to do this in C, I believe C++ now uses a sensible, secure random number generator, but I don't think the standard guarantees you that. So I'd suggest you use libsodium random bytes or something of that ilk. And obviously don't seed it with a number of ticks since boot or whatever. Modern hardware should have plenty of sources of randomness. I think it's been built into chips, and maybe even the Pentium had a random number generator. Yeah, you need to really get some randomness in there. So I guess slightly more mathematically interesting. In the first example we talked about, they were using a static key, but also they were using GCM with a repeated IV, which means that you can decrypt stuff even if you don't know the key, because, say, I know one of the passwords that's in the database, and I know the decrypt of that data, because I've got the database itself. I can see what the encrypted password is. If it's my password, I can see what my plaintext password is. So if you run GCM or any stream cipher, if you keep the same key in IV, you will generate a fixed key stream, and you'll then basically the effective operation is XORing your data with that key stream. So if I know an encrypted piece of data and a plain text which match, I can XOR those two, and I can recover the key stream, and then I can decrypt any of your data up to that length, obviously, which is why it's basically described as a catastrophic failure. It means that none of the data in your database is necessarily guaranteed to be secure. This one it's a little bit harder to explain, and it took me way too long to implement it. But essentially, here we've got the known cipher bytes. So I know my password is password 1. That's what it is encrypted at the top, and then it is stored as a length and then thing. So it's 0009 password, because it's stored as a 32-bit int. And then you have some unknown ciphertext, which is maybe someone else's password. So I've omitted the code to pad these all to the same length, but then we simply iterate over. I traverses like just one up to the end of the first string to run out, and we take the byte from our known ciphertext, which is my password encrypted in the database, the known plaintext, because I know what my password is, and we XOR those two. That gives us the key byte for that position. And then, because we've got the key, we can just XOR again the unknown ciphertext and get the decrypt. So yeah, this works fine, and in this case it's decrypted the test data to 0008 password, because it's obviously one byte shorter, and yeah, just some other user can then access that encrypted password. Obviously, how big a problem that is depends on what the application is and who's using it, but in some cases it can be a really major problem. So this won't be much to look at, and it's slowed down. It's just doing one byte at a time, so it's inferring the keystream byte from the known stuff, and then it's using that keystream byte to decrypt the unknown thing, and hopefully we'll get to that's the decrypted password. So again, even if you didn't know the static key here or the key derivation function, if you knew they're using AES-GCM with a fixed key and IB, and you knew these other 2 bits of data, you can decrypt stuff. I wonder if I can pause that there. I guess the upshot is someone's gone, AES-GCM, that's secure, we'll use that, and then probably not had enough experience to know some of the pitfalls that can bring. So, I think I've already talked about this really. There's other stream cipher modes like OFB, output feedback mode, and counter, where reusing the IB causes that same problem. If you know an encrypted thing and the plaintext, you can derive the key again, and then you can. We saw this in a web app where the cookie is essentially just an encrypted blob. But if you saw the source code and you knew obviously you know your login name, you know what the plaintext is, you know what the ciphertext is, you can compute the key stream, and then you can just forge cookies as anyone you feel like. So the key thing to remember, that AES-GCM, Galois mode, really breaks quite hard if you use a fixed IV. They'd have perversely been better off with the older primitive AES-CBC, which has problems, but not such catastrophic problems. I think I briefly touched on HMAC before. So this is a hashed message authentication code, which means you want to tell if a message that has been constructed, you want to verify that it is true, i.e. it's been constructed by your intended counterparty and not some random bloke in the middle. So the construction is to use a hash function of the key plus a hash function of the key and message. And that was arrived at after some other things turned out not to be quite as good as you might want and have ways of forging like length extension attacks. So HMAC SHA-1 is defined as that. It works. Even though SHA-1's considered a bit broken these days, HMAC SHA-1 does what we want it to. I.e., your two parties know the secret. They will do this hash operation, and then both of them can tell that the other one, because of the shared secret, the other one generated that message. And just going right back to MOXIE, you need to check the message authentication code before you try to do the decrypt. So in this particular web application, they were using HMAC to, the cookie basically said the username is this, and the checksum is HMAC, which is all very well up until you leak the secret, and then anyone can make a cookie again as anyone. And this is probably worth highlighting, because if you just use PHP session ID, you wouldn't have had this problem. But because you've tried to be clever, it's given you a false sense of security. And again, it's all very well until a secret is not secret, and then it really breaks catastrophically. So a couple of the things we've seen. Sorry, let's skip one. We've seen people, for some reason, on an embedded device, they implemented it was essentially just see SHA-1 do assault and pass, and you can crack that with Hashcat. They've done it 1,000 times. It makes it a little bit slower, but you could have saved yourself effort and just use bcrypt, like a modern hashing thing, rather than inventing a homebrew scheme. And again, in that application, someone just put a magic prefix into MD5 and a suffix. John the Ripper, you can just write a rule to replicate this, and then just crack it with a normal word list. So again, they've gone to a lot of effort when they could have just used like a bcrypt type modern primitive. So just summing up. Try not to write your own crypto. A lot of people have written it and then found it's lacking, and it's very hard to construct a crypto system and then find bugs in it. You also kind of need to understand what you're defending against. Like some of these flaws may not be an issue in some circumstances. Also, secrets, absolutely, obviously they need to stay secret. They can't be predictable, so and they can't be guessable, and they should take up the entire key space. So, like we've seen, we can if we know the search space is confined to a particular a subset, we can just search that and we can get that out really quickly. Whereas everyone thinks that they're fine and they've got 128-bit key and everything's great. The other thing we come across everywhere is secrets stored in source code. A, it's really bad because everyone can see them. B, it means they're the same across every instance of your software ever. And it also makes them really, really hard to rotate, so should they be discovered. So yeah, just please don't use any other way of doing it than this. There's key vaults in AWS and everything, and DP API on Windows. So nonces, IBs, and sorts are really important. And you find people just sort of copy this stuff off Stack Exchange or something, and they've written IB equals whatever, and that gets copied into someone's program code, and it's not appropriate for whatever they're trying to do. And the other thing is this is a terrible thing to find in pen test, because I know a lot of this stuff will need a substantial rewrite and then a retest, and it would have taken a lot less time if someone had been able to address it at the design stage. rather than doing like a week's pen test and then another week's free test, doing it right first time would have taken maybe a couple of days. The other thing that tends to creep in that people try to overcomplicate the designs. So like there was a recent crash FTP bug where they'd try to overload some stuff and they'd end up with quite a complex if statement which had missed one of the edge cases. So I do also want to talk about this. You can create a per install, like so for a web help desk software. You could create a key, put it in DP API, everything's fine. What if your machine crashes and then you need to put it on your box? Then you might not be able to restore the backup. So you do have to think about these things. Obviously, the more you encrypt things, the less available they are. Should you need to do something slightly different. So there is definitely a trade-off there between confidentiality and availability, and that needs to be part of the design planning. Like, do you want it so it will only ever run on this box with this backup? And then, like I say, for the DRM problem, you can't entirely fix it because obviously computers can be emulated and everything, but you can make it harder for people to recover some of this data. I'll put some references in here. My favourite book is Serious Crypto by J.P. Ormison. There's a reference for the keystream recovery attack. Which again goes into a lot of detail, but I'd say the long and short is that you can recover the keystream. Laticora's cryptographic right answers is very good as well. And then there's a few discussions of Argon 2 versus bcrypt versus script and various things. So that's it. Are there any questions? Feel free to write them in email if it's okay to later on. Oh yeah, sorry Nick.
Hi, thanks James. Good talk.
Thank you.
When you found this stuff, is it normally present in older code, or is it just still there in newer stuff? An indication of lack of awareness?
Yeah, it is still present. I mean, the examples are mainly from like CV 2024. That was like December. So yeah, that was current code. Just by virtue of the fact it had GCM in it, it must be relatively recent. So yeah, some developers probably just had like target item encrypt this password, and they've probably just done something, copied it off Stack Exchange like we'll do. And it's very hard to explain the complexities of how it should work if you're trying to keep a secret safe from other users of the system as well as everyone outside. So yeah, it's definitely still happening. When I do code review, I tend to crypt and then go from there because there's other tools to find the rest of it. But sorry. Oh, yeah.
Have you started advising your customers start switching to post-quantum?
We haven't, no. And no one's asked. So it's something I'm going to have to look at some point, but I have not got there yet. Yeah.